Let's talk about our project, Whole Body Dynamic Controller for Valkyrie. The goal of this project is to achieve position and torque control, static stability, and whole body control of the Valkyrie R5 robot. These figures show the results we got for the COM and the support polygon. The green boundary indicates the support polygon and the red dot indicates the projected COM. Our stability criteria was to keep the projected COM inside the support polygon. The figure on the left shows a stable pose and the figure on the right shows an unstable pose, where the projected COM is outside the support polygon. We achieved joint level control using ROS control, where each joint could be commanded for position, velocity, and torque. Controlling 32 active joints makes the task of developing a standing controller very challenging. There is always coupling between joints which causes disturbance, and determining the correct PID gains for all joints is a Herculean task. That's the reason we decided to reduce the joint space to 12 degrees of freedom. So now we consider only the lower body with 6 degrees of freedom in each leg. We implemented and tested a total of 3 control approaches, which was the spherical inverted pendulum, the set point tracking for COM, and the whole body operational space control. In the spherical inverted pendulum, the COM is considered to be the blob of the pendulum, which is pivoted at the ankle via a massless rod. This technique removes the constraint of not having to maintain a constant height for COM. However, this technique can work only for lightweight robots as it involves balancing using only ankle joint control, which is not practical for a robot like Valkyrie due to its heavy weight. In the set point tracking approach, we set the COM at a stable position in the support polygon and track it using a simple PD controller, which is realized using inverse kinematics and inverse dynamics. The drawback of this technique is that it is not robust and depends on initial conditions and precise gain tuning. We realized that the problem at hand was achieving multiple goal objectives at the same time. For example, for the robot to stand, the objectives would be keeping the COM within the support polygon, orienting the chest in an upright manner, and whole body control using torques and position. The solution to this would be a hierarchical control policy which involves assigning priorities to tasks. This can be achieved using whole body operational space control. The standing controller is achieved by using whole body operational space control, which is realized using the control it framework. The control it framework allows us to set constraint primitives, task primitives, and posture primitives as mentioned on the slide. Now let's see the robot in action. In this video, once the robot is released from the harness, as seen, it goes into a stable position. To check the stability, we shift the COM to another position, and as seen, the robot shifts the COM to other position while maintaining stability and it does not fall. This graph shows the positions of the 12 joints varying with respect to time. As seen in the graph, the joints are at a certain position when the COM is in a stable position. The position of the joints change in a very orderly fashion when we command the COM to move to another position. This indicates static stability.